welcome to the High Energy Seminar. Today our first speaker is Kate Alexander, and she is currently a 6-year graduate student at Harvard. She's working with Professor Ethel Berger, and her research interests focus on the time domain and astrophysics and cosmology. And before she came here, she was an undergraduate student at Brown University, and she did a RU program at the Center for Astrophysics. So the RU program is really a successful program. Today she's going to talk to us about the radio counterpart of the GW 70817.
Thank you very much. So yes, since you mentioned the RU program, I'd actually like to credit the RU with first getting me interested in radio astronomy and time domain projects. And now here I am presenting on this wonderfully exciting event as part of my thesis work. So great job on the RU. So we've all heard a lot of talks on GW 170817 over the past couple of months, but just to make sure that we're all on the same page, I wanted to start with a little bit of background. And I'm going to be focusing on our follow-up as related to the fastest moving ejecta, so it won't be a talk on the kilonova mission that we've all heard so much about. But as we know, LIGO and Virgo found gravitational waves from several different types of sources. There's a number of black hole binaries shown in the upper part of this plot. And then 170817 is a neutron star binary, which was 2 neutron stars that are fairly consistent with the typical masses of known neutron stars that merged to form what is probably the smallest black hole that we are aware of. So we already are very excited about this picture from gravitational waves. But as an astronomer, we're also excited about the types of electromagnetic counterparts that we can observe from these kinds of mergers, because that gives us a completely orthogonal set of information to learn about these compact objects. So as we all know, the optical emission is one of the most promising counterparts to these things because it's fairly isotropic. This is the kilonova emission, but as a radio astronomer, I'm interested in what kind of radio counterparts can you get from these sources. And there's 2 sorts of different similar emission procedures that operate on different timescales. The slow-moving, in this case, a few tenths of % the speed of light is slow-moving, emission or ejecta that produces the optical emission on very long timescales, years to decades, will eventually slow down as it interacts with the medium around the binary. And as it slows down, it'll produce a shock front that generates non-thermal emission that will peak in the radio band. But we don't want to wait for years and decades to start observing these things. And fortunately, it's predicted that many, if not all, binary neutron star mergers will also generate a relativistic jet of material, which, if we view it on axis, will produce a short gamma ray burst, but also produces broadband afterglow emission. And if the jet is initially pointed away from us, all of this emission will initially be relativistically beamed, but the jet will also decelerate on a much faster time scale. So depending on the viewing angle of the observer, we should start to see this emission anytime from almost immediately after the gamma ray burst or the gravitational wave trigger to several weeks to maybe months afterwards. So this is what the afterglow spectrum of a typical gamma ray burst looks like. This is a very broad band spectrum, and it's characterized by various power laws and a series of break frequencies that move from high frequencies to low frequencies. And so if you observe over a wide enough wavelength range, you can, to capture all the different break frequencies, you can then back out the physical properties of the material that's producing the shock, that's producing the synchrotron emission. So you can get constraints on the energetics of the outflow, the density of the surrounding medium, and the shock parameters. As I mentioned, this is a very broadband spectrum, so to fully capture the behavior of the SED, you really need observations from radio all the way to X-rays. And in particular, for something that's off-axis initially, by the time you're seeing this emission, the peak of your SED will be in the radio band, or even below the radio band. So the radio is the best place to look. However, that doesn't mean we shouldn't look elsewhere. We have some very sensitive X-ray telescopes, notably Chandra, which is of great importance to a lot of people here, that actually could be sensitive enough to detect emission, even though it's much fainter in the X-wave in the radio band. So for binary neutron star mergers, the optical band is going to be dominated by this kilonova emission. So if you're interested in the most relativistic material, you really want to look at the radio and the X-rays, especially at the earlier times. So as everybody knows, we really hit the EM jackpot with GW 170817. This figure on the right is just meant to illustrate the scope of the follow-up campaign that was undertaken for this object. We had observations taken from high energy all the way down to the radio band, starting everywhere from 2 seconds after the burst, where we detected a weak burst of short gamma ray emission, all the way out to weeks afterwards. You'll notice most of the optical and UV-IR follow-up stops about 2 weeks after the event. That's because the event became a daytime object, so it's too close to the sun for X-ray and optical telescopes to observe. But in the radio, we were able to keep going because radio telescopes can work in the daytime. And so I'm going to focus on our group's X-ray and radio observations of this event. However, before we could start X-ray and radio follow-up, we had to know where to look. And radio telescopes are wonderful, but they're ones that have the most sensitivity and resolution are interferometers, which means their field of view is tiny. So you can sort of try to do a radio survey where you target nearby galaxies, but the most efficient way to tile over a large area of the sky is in the optical band. So we use the dark energy camera to cover 80% of the final LIGO localization region for this source. And we detected one new transient that appeared on the timescales of the detection of gravitational waves, which is the now famous kilonova counterpart in NGC 4993. So once we had this precise location, which we got within 11 hours of the discovery of the gravitational waves, we then immediately triggered deep multi-wavelength follow-up. So initially, we didn't detect anything in the X-rays. We were able to get Chandra observations in just over 2 days. And you can see the orange circle up there is the location of the optical counterpart. And there's initially no X-ray emission. And then in a follow-up observation taken almost 2 weeks later, there is X-ray emission has appeared. And the first X-ray detection of this source occurred at about 10 days. So this is already consistent with something somewhat off-axis, but not terribly off-axis. We also triggered radio observations starting immediately after the burst. So this is our very first radio image of the field of view of the transient. You can see that we detect emission from the center of the host galaxy of the transient, which we think is consistent with a weak AGN in the galaxy. But we don't detect anything at the optical position of the source. And the reason this image looks not so great is by the time we had localized the source, it was just about to set at the Very Large Array in New Mexico where this image was taken. So we coordinated with the schedulers to find out exactly how much time we had before it sank below the horizon. We were able to get on source for 20 minutes and collect this image. But so it was a lot of fun. And the VLA schedulers were really very supportive of us through this entire campaign. But this early upper limit ruled out that we were viewing a relativistic jet on axis, which some people initially thought we might have been because of this detection of gamma rays, which turned out to be much weaker than typical gamma ray bursts, as I'll get to. So initially, we continued to not see anything in the radio until about 16 days after the event. And then as the X-ray emission started rising, we also saw a radio emission that started to rise. And we also observed this source with ALMA and didn't detect anything. So since there was gamma ray emission from this source, one immediate thing one can do is compare this source to cosmological short gamma ray bursts, which are also thought to come from binary neutron stars, and see whether this one looks similar or different. And you can see immediately that the X-rays and radio detections of this source are very different from the cosmological short GRB population. In particular, they're a lot fainter, and they show a rise at late times. So all of the on-axis short gamma ray bursts show declining X-ray emission or much brighter radio emission when the sources are detected. None of them show this emission that rises at these late times. And so to show that in comparison with some models, this is our observed broadband SED at 2.5 days, the time of our first Chandra upper limit. And a typical short gamma ray burst afterglow at this epoch would be two possible models of the black lines. You can see that these upper limits very clearly rule on this on-axis thing with a typical energy comparable to short gamma ray bursts. You could hide a very weak short gamma ray burst afterglow underneath these upper limits. So the isotropic equivalent energy in the gamma rays from this particular event was only about 10 to the 47 ergs or so. So if you had an afterglow with that energy, it would be these lower colored lines down here. However, that afterglow would fade away. It would not be predicted to rise at late times. So in that case, the radio and X-ray emission that we see would have to come from something else. So in short, we rule out, just from our first couple days of observations, a short GRB-like on-axis jet. So, as I've already said, the next obvious thing to consider is, well, it's unlikely that we would be observing directly down the barrel of the relativistic jet. So what if the jet were initially pointed away from us? What then would we expect to see? What kind of timescales would we expect the radio and X-ray emission to appear on? So to do this, we turned to numerical simulations. So this is a set of simulations developed by a group at NYU, led by Andrew McFadden. And these jets are a uniform conical jet, top hat jet, expanding into a uniform density medium. And then you can pick any viewing angle you want and integrate along the line of sight to figure out what your light curve should look like. So we have been developing a very broad series of high-resolution simulations runs of this code to explore what parameters are consistent with our observations. And we've been varying the energy in the jet, motivated by the ranges seen in short gamma ray bursts, the density that the jet is expanding into, the viewing angle, and then also the microphysical shock parameters. And this is what we find. So on the left, we have off-axis light curves for an optimistic and the pessimistic model for the emission you would expect in the radio band at 10 gigahertz compared with our early upper limits of this source. So you see for more energetic, for a more energetic short GRB, we really rule out quite a broad range of viewing angles. But if the jet is less energetic, then we're maybe consistent with something that is observed at about 20 degrees or 40 degrees off axis. And then on the right here, we have both our radio light curve and our X-ray observations as published in our first series of papers on this object, just showing that this kind of model with a density of about 10 to the minus 3, an energy of about 10 to the 49 ergs, and a jet opening angle of about 15 degrees, viewed at an off-axis angle of about 28 degrees, is roughly consistent with our observations. So in short, this we can find that the radio and X-rays are consistent with an off-axis relativistic jet that looks very much like a typical short GRB, just we're not viewing it directly down the jet. We've, of course, considered or continued observing this source in the radio since then, and we actually this week are getting new Chandra observations, so there will be another point on the X-ray light curve coming soon. So we've continued to tweak the model a little bit as more radio data has become available, but you can see from these light curves that the radio and X-ray observations today are still broadly consistent with an off-axis relativistic jet. Now, this is not the only model that has been proposed to explain the X-ray and radio observations. In particular, work led out of Caltech by Greg Hallinan and Kunal Mooley and others has proposed that in some binary neutron star mergers, perhaps rather than getting a relativistic jet, there is too much material immediately surrounding the merger, and so the jet is choked before it can get out. And so instead of an extremely relativistic, narrower jet, you get a broader cocoon of material with an initial Lorentz factor of about 2 to 3. And so since this is a less relativistic outflow of material, the emission takes longer to rise, and you can get a model that is their red line or the black dotted line here are two different cocoon models, which also do a pretty good job of explaining the radio light curve at 3 gigahertz. Another possibility is that this isn't ultra-relativistic material at all. Instead, the material that produced the kilonova emission, we know most of it is moving at about 10 to 30% the speed of light, but there might be a high velocity tail of the ejecta going up all the way to, say, 0.8 C. And it turns out you can have that match the radio observations to date so far as well. This is the blue dashed line here on this plot. Now, the interesting thing is that all of these models make somewhat different predictions for the future evolution of the radio emission. So as you can see, all of these models kind of predict that this emission should continue to rise for the foreseeable future, while the relativistic jet models, including the one I showed here, predict it should start to fall off and decline. So as we continue to monitor this source in radio and X-ray bands, we should know over the next coming months which of these models is likely to be correct. And then if it turns out that not all binary neutron star mergers successfully produce relativistic jets like we've seen in short GRBs, that has interesting implications for the rates, possibly. So our group has put together this multi-wavelength follow-up campaign, as I've mentioned, to continue observing this afterglow component of the relativistic ejecta. We've been able to continue observing with the VLA all the way through sunblock, and we just got more time approved to keep following it for through the next VLA cycle, which is very exciting. And then as we speak, the latest observations with Chandra are being completed of this target now that it has reemerged from sunblock. So stay tuned over the next couple days. We should have exciting new results from that coming soon. And then another interesting thing is that now that the kilonova has faded away over the past couple of months, we actually expect that the part of the afterglow and the optical and near IR band should now be barely detectable with HST. So, or easily detectable for some of the ranges of models. So we also have HST observations approved that we're getting later this week as well. So pretty soon we should have a very nice SED of this component that includes optical data for the first time. So that's also very exciting. And then this target is not going to go away anytime soon. As I mentioned at the very beginning of the talk, the slower moving ejecta that originally produced the kilonova emission in the optical will eventually decelerate. And we expect that even if this initial component from the relativistic jet fades away, we should see a radio rebrightening of this source on timescales of 5 to 10 years. So the blue shaded region is the emission from the blue kilonova component for the allowed range of, for the density range allowed by our radio modeling of the relativistic ejecta. This range will shrink as we continue to get better constraints on that with our current radio modeling. And this is just a very simple toy model. But you can see that with the VLA at its current sensitivity, this is the solid black line, this component should be sort of barely detectable. But on timescales of 10 years or more, we should have the next generation of radio telescopes coming online. And so then you have a much better chance of detecting this component with ongoing radio facilities. And in fact, this is suggestive that sources like this will be showing up in deep, ongoing radio surveys of the sky. So unlike optical and even X-ray observations to some degree, there really isn't a deep radio time domain survey of the sky that exists over the whole sky yet. Because if you want to do that with high resolution at centimeter wavelengths, with an interferometer, it's a tiny field of view, so it's very, very expensive to do this kind of survey. So the VLA Sky Survey is starting now, and this is something we're very excited about because it will be the deepest map of the northern sky taken to date, and it's predicted to detect almost 10 million extragalactic sources, and it's going to have a couple of epochs. So there will be gravitational wave counterpart, radio counterparts in that survey probably, but identifying them may be a challenge. And then, of course, every radio astronomer who gives a talk has to mention the Square Kilometer Array, which is being built, and the scope is being decided right now. And the Meerkat Precursor Array has already come online. This is the first light image. It doesn't show up terribly well, but the circled objects were the only 5 sources known in this field before this first light image, and there's a couple of hundred sources in this field. So this is just a taste of what the upcoming era of radio astronomy will have to offer. So as I mentioned, these new radio facilities are going to be a valuable resource for finding gravitational wave components, but the problem is the rates. So this is just a plot showing expected rates for known categories of radio transients. They're all fairly low. As you can see, there's a lot of upper limits from smaller scale radio monitoring campaigns that have been done to date. The VLA Sky Survey will be all the way down here. So it'll be starting to probe the rate of binary neutron stars, but we'll have to make sure we can distinguish them from other types of sources like supernovae, tidal disruption events, other things we may not have thought of yet. So part of the rest of my thesis has been working on studying other kinds of radio transients and attempting to better characterize the known populations, which will continue to be important as radio astronomy transitions from a follow-up of transients discovered at other wavelengths to discovering transients at the radio band and really moving forward into this era of time domain astronomy that's already been achieved in optical facilities. So that's about all I wanted to talk about today. I'll leave my conclusions up and continue to advertise our group's website, kilonova.org, which despite the name also has results from our follow-up of the non-kilonova components of the emission from this event, which I hope I've convinced you are just as interesting. Thanks.
So you said that the radio emission under the top hat model is sort of a 28-degree off-axis observer position. Is there support for other angles, like at 10 degrees or 40 degrees or something?
Yeah, so that model I showed was from our first round of papers, and we found a couple models that produced comparable fits, and they kind of range between about 20 to 40 degrees. So I'd say that there's still support for roughly that range.
It would be interesting to show like posteriors for that kind of model, like compared to the gravitational wave data.
Yeah, so there's actually a paper that our group has been, that just got accepted to AppJ Letters, where we take those kind of priors and see if you can get tighter constraints on H0 when you fold in information from the EM constraints as well. So that paper is led by Cristiano Guidorzi, and I encourage you to check it out if you're interested.
Probably I misread it. The X-ray image you showed, there seems to be another source brightened the SP.
Yeah, so you're correct about that. That's discussed in Raffaella Marguti's paper of the initial X-ray follow-up a little bit. So there is this S2 source, which also seems to turn on. The initial, so if you look at the initial Swift XRT localization, where they didn't really detect X-ray emission early on, but there was like a question about it. It's possible that this source is a variable source that had turned on at the time of the first localization there, which was prior to 2.3 days. But yes, that we think is just a coincidence, and there's a calculation of the probability of that in Raffaella's paper.
Are you trying to do imaging in radio with VLBI?
So we are not. Another group is. The reason we haven't so far is it just hasn't been bright enough. In our most recent observations, the brightness of the source was about 40 microjansky, which is pretty faint. If you go to lower frequencies, it's a little bit brighter, but the source has continued to brighten over the past few months. So, so far, I imagine the group that is doing the VLBI hasn't gotten anything terribly interesting out of it yet, but if it continues to get brighter, then it's definitely something worth considering.
If you use the phased VLA, really good telescopes get the same sensitivity, more or less.
Yeah, I mean, well, it would be interesting to go through and do the calculations and figure out how much lower resolution you'd get in combination with phased VLA. But yeah, I do know there's another group that's already been taking a look at that.
So is there a third Chandra epoch, or is that the one that's in the schedule this week?
So there've been there have been 4 Chandra observations prior to this week. There are these 2, which were led by our group. There was another one 5 days before the 15-day one, which was the first detection, and there was another one 24 hours after our observation, which showed a comparable flux. And then the observations that are being taken this week are going to be shared with multiple groups who are all interested in continuing to observe this source. And if it's detected, I'm sure we'll be asking for more time. So hopefully the Chandra Committee continues to think this is interesting as well.
Question. What was the time delay between the gravitational wave and the gamma burst?
1.7 seconds. So yeah, people are writing lots of theoretical papers speculating why that might be so, and my understanding is there's not a consensus on that yet.
Any other questions? Not the same cake. Our second
Thanks.
speaker is Dr. Tremblay. And Grant is currently an astrophysicist at Harvard Smithsonian Center for Astrophysics. And he got his PhD in 2011
Yes, good call.
Texas Institute. And after that, he became a ESO fellow at Munich, and he spent 3 years there. He was also an astronomer at ESO Chile. And after that, he became a NASA Einstein fellow at Yale. Then today he's going to give us his first official talk since he joined CFA.
I think my second. Yeah, sure. Yeah, sure. So it's technically my second talk, and this time I'm not talking about my science, but not because I recently spoke about my science here. It's because after the first LIGO detections, I realized that I would never again talk about my science after a LIGO talk because there's no way it will be as cool. So instead, I'm going to talk about an instrument that I helped commission while I was working at ESO at the Very Large Telescope, Paranal Observatory in Chile. And this is kind of brought about partially by seeing that Kate was speaking and then realizing that I wasn't going to talk about my stuff, but also because I was asked a couple of years ago to contribute to a NASA committee whose goal was to increase our community's familiarity with integral field spectroscopic data, right? So I'm talking about not just an image of a galaxy, but every pixel in your image is a spectrum, right? So it's a three-dimensional data cube where you have 2 dimensions of sky and then 1 dimension of wavelength, or effectively velocity, right? I don't need to convince the people in this room that multiplexed spatially resolved spectroscopy over a 2D field of view is a very powerful technique, right? We do it every day with Chandra. Chandra is effectively an IFU. The first IFU ever in space, arguably. I guess you could make some arguments about Einstein depending on the spectral resolution, but anyway. Yeah, it's an incredibly powerful technique, but it's also really worrying, right? Because basically every single astronomer, even our theorist friends, know how to open a Fitts image in DS9, but a lot of us have never worked with a proper 3-dimensional IFU data cube, right? And there's no obvious go-to solution to analyze this stuff, right? There's QFitsView, there's some 3D functionality built into DS9, but otherwise you're kind of working with your own homebrew solution if you're not using things like CasaView or things like that. And that's really worrying to NASA because we are about to launch a $200 million integral field spectrograph on a $9 billion space telescope that will last for about 5 years, right? This is NearSpec that's being integrated in this photo into the Science Instrument Module of JWST. NearSpec does many things, including multi-object spectroscopy, but at its core is a microshutter array, this beautiful microshutter array that is an IFU. And it will be really a huge driver for a lot of JWST prime science. And the thing about JWST that we all have to remember is that it's a tennis court sized thing orbiting around L2. It's a tennis court, so its moment of inertia is ridiculous. And that means that managing the angular momentum budget of the spacecraft is super, super expensive, right? Because you have to station keep around L2. And so the problem is that the mission lifetime is hard capped at 10 years. It's nominally aimed at 5 years, but the spacecraft will absolutely run out of fuel in 10 years. And so the JWST cycles, for being such exciting science, right, 10 Nature papers, written every observation, this cycle's going to be super quick, right? Chandra's 2 decades old. HST is 26 years old, right? There's been plenty of time to get your data out in cycle 18 and publish it in cycle 23. But with JWST, you got to get your data, you got to publish it, and inform cycle 2 and cycle 3 and cycle 4 and cycle 5, and then you're done. Or hopefully we get to cycle 10, but you know what I mean, right? So NASA's really worried that the public doesn't really know how to deal with integral field spectroscopy on a large scale, right? And that's because the technology is pretty young. Throughout this talk, I'm going to ignore X-ray telescopes and radio receivers. You could argue that a heterodyne radio receiver mounted on an interferometer is effectively an IFU. Chandra is an IFU. But for the purposes of this talk, I'm talking about optical and near-infrared integral field unit spectrographs. And that technology is really young, right? So that it was first proposed by George Korte in 1980. This paper was actually published in 1982, but he had the idea in 1980. And if you read this paper, it's beautiful because he's totally pitching it for a space telescope, right? Here at the bottom here, he's talking about HST, and he was way too late to get aboard HST. The instrumentation was well set by 1982. But it's really, really remarkable to know that that this sort of idea is now flying in a $200 million realization of that technology on a really flagship mission. And so IFUs are now a thing, right? So that's becoming clear. And so for my first postdoc, I was a fellow at the European Southern Observatory. And the weird thing about that fellowship is that you have a mandated 25% duty component. People applying to postdocs are kind of scared by that. I think it's awesome. So I was living in Munich, but every other month I had to fly to Chile, which sucked. But I got this really incredible life experience of, I operated Unit Telescope 2, the second one there. But I got to be involved in the commissioning of my favorite ground-based instrument in the world, which is MUSE, right? It looks like an espresso machine from hell, right? So I'm going to talk only about MUSE for the rest of this talk and not really show any results, but just like really brag about the instrument because I think it's really special. And I think it is the perfect illustration of the fact that integral field spectrographs have advanced to over an increment that I think is comparable to the transition from photographic plates to digital imaging, right? That seems like a pretty heavy statement because that was a major transition, but I think it's pretty fair if you consider that if we look at how observational techniques have advanced over the past 3,000 years, right? So this is the Nebula sky disk. It is the first known depiction of the night sky that wasn't a sun like drawn on a cave. And then there's apparently some moons, apparently like drilled into some bones, but it's unclear whether it was like moons as a calendar or like some violent thing happening. So this is the first known depiction of the night sky. It has the moon phases. It has beautiful 82-degree arcs between the solstices, which is lovely. It has the Pleiades, which is really cool. And of course, this is a 4,000-year-old thing from the Bronze Age, and so it came like next to some swords. So of course, right? But you could argue that this is basically a sketch, right? The first astronomical sketch. And that didn't change for thousands of years, right? This is the first sketch of spiral structure in what was then called a nebula. Of course, it's M51. This is the first sketch of spiral structure in a galaxy. And notice the date is 1845. So thousands of years after the Nebula sky disk, we were still sketching, right? Galileo revolutionized astronomy, right? But he was still sketching the moons of Jupiter, right? So that didn't change for thousands of years. And so astronomy for thousands of years was dominated by a super primitive technology. This is the very first astrophotograph, right? It was taken by the 11-inch Henry Draper telescope with a photographic emulsion. This is 50 minutes on source, 1880. This is 1 second with an iPhone 4S. In 2013 through some binoculars, and they look really impressively similar, actually. And so the point is that digital imaging completely changed everything, right? This is the first digital image ever taken. That's 1957, and then we were beaming the first digital image from deep space only 8 years later. This is the first image from Mars orbit. That's pretty astonishing, right? So this is a photo I took I was touring the Burikhan Observatory in Armenia. It's a beautiful, like, Soviet-era piece of art. But they still use these 128 megabyte things. They're the size of a Buick. And I think it's 7-track FITS format that they store in these tapes. This is a 2 terabyte micro SD card, so 15,000 times more space and 15,000 times smaller volume, which I thought was pretty cool. This is arguably the first like really good spectroscopic result, right? This is the detection of the interstellar medium made with a great refractor in Potsdam in 1902. They were looking at a close physical pair, so 2 stars orbiting one another. The lines emitted from the stars move in velocity space, but the calcium H and K lines didn't move, right? And so that must be from some medium between us and the stars. It stayed still. That was, of course, the interstellar medium in the Milky Way. And then it was about 100 years later that we're doing spectroscopy of a redshift 11 galaxy, which is something like 500 million years after the Big Bang, right? So 100 years there, okay, fine. I promise I have a where I'm going with this. I have a direction. This is my favorite figure from any paper ever. This is the first interferometric map of a radio galaxy. I think it's beautiful. It's from Jodrell Bank, 1953. This is the actual source that it is. It's about 25 years to get from there to there. This is Sig A, of course. Yeah, so we're talking about 150 years to get from a sketch from Charles Messier of the Orion Nebula to an HST image. This is my favorite thing ever. This is the first N-body simulation from Holmberg in 1941. If you haven't read that paper, leave right now and go read it. It's one of my favorite papers ever written. Holmberg brilliantly used light bulbs screwed into a board. I can't remember how many. It was like on the order of 16 or so. So the light bulb, the candle power of the bulb is proportional to is like a proxy for mass, right? And then he used a photocell, a photometer, to measure the flux, which of course falls off as 1 over r squared, which is gravity. And he did a really rudimentary but really beautiful N-body simulation of a tidal interaction between 2 galaxies. Absolutely spectacular, right? And then so 75 years to get from that to illustrious TNG done in-house right here, right? So the point of all of this is to kind of like frame the context over which integral field spectroscopy is developed. Prior to 1980, what would you do if I wanted to ask, well, let's learn the most that we can from this, from a single observational technique, right? Well, so the most that you could learn from it is to do not only photometry, but spectrophotometry, right? Spatially resolved spectroscopy over this entire thing. The pillars of creation are 3 by 3 arc minutes on the sky, so they're absolutely enormous, keep in mind, right? So what would you do before 1980? You'd take a long slit, right? Long slit, I'd maybe do drift scan, I'd maybe do MOS, but I would do an observation here with my long slit, and then I'd do it here, and then here, and then here, and then here, and then here. And then that is like sort of like that is integral field spectroscopy, right? You sacrifice, of course, one spatial dimension along the dispersion axis, but you get spatial information along the long axis. So if you stack your slits long enough, you can cover the whole nebula. It might take you 4 years, but, you know. Prior to 1980, you could also be smarter, and you could effectively do a stacked series of narrowband imaging, right? So I can image the nebula in one wavelength and then another closely separated wavelength and another one, stack them. That's sort of rudimentary integral field spectroscopy. You could do this more smartly with a Fabry-Perot or a tunable filter. A Fabry-Perot is effectively a tunable filter where the band pass is really hard and set by an interferometric fringe. But the data reduction is an absolute nightmare. You can't flat field the thing. The seeing varies, and it takes you like 20 nights to actually take your image because you have to take many separate observations. It's not a simultaneous thing. And then finally, you could do an FFT. CITEL, in case you've heard of it, CITEL is an FFT Fourier transform spectrograph on the CFHT. That basically places a Michelson interferometer in the telescope light path, and then you change the delay line by moving this mirror, and then you image you create an interferogram by imaging the fringe, and then that fringe could be Fourier transformed, and then you effectively get spatially resolved spectroscopy over this thing. The long story short is that it's really, really hard to do before 1980. After the development over the next 30 years or so of integral field spectrographs, there came like 3 flagship ways to actually do this. You could pack a bunch of lenslets into the focal plane and then pipe that light into individual spectrograph inputs, right? So that kind of breaks your field down, and then you get a spectrum from each one of those lenslets. You could couple in. So that's hard because packing lenslets into the focal plane array necessarily means that you have to have really crappy spatial resolution because you can't have super tiny lenses on the scale of a pixel, right? You can do a little bit better with fibers, but really the best way to do it is to remove all your stuff from the focal plane and keep all of your stuff that makes the IFU further down the optical path. And that is what a slicer does, and that is what this instrument I worked on does, called MUSE. So again, this was 3 by 3 arc minutes on the sky. You could do this with say, a lenslet, a multi-lenslet array, or a fiber-fed spectrograph, but the spatial resolution would be really crappy. If you wanted to image it with prior to MUSE, the best IFU in the world, that would be, for example, the GMOS one-slit IFU on Gemini North and South, right? But the FOV is 3.5 by 5 arc seconds, so that's that little square up top. So if I wanted to take GMOS across the entire Eagle Nebula, that would be a pain, right? Each of those observations are maybe an hour. You have to nod to sky and back to back, disaster, right? I went a little aggressive with my squares here. Anyway, the long story short is that we commissioned MUSE. It's the greatest ground-based instrument ever built, with apologies to anyone who's worked on another ground-based instrument. Here it is again. And it's like prime motivating thing is that it has a 60 by 60 arc second field of view, 1 by 1 arc minute, at the seeing limit. So if you know anything about IFUs, that should really astonish you. Here's how it works, basically. This image, okay, this movie goes too fast, so I have to, okay. I'm gonna like speed up and really quickly talk through every step. So like, bear with me. All right, ready? Go. Okay, so the image goes through a derotator, which compensates for the rotation of the Earth. And then the image is then magnified, and then its aspect ratio stretched. And then the image is then divided into 24 separate beams. So that's dividing your field of view into 24 slices. Each of those 24 slices are redirected off one of these 24 mirrors, which then pipes it to 24 independent but linked IFUs. So here's an example for one of those IFUs. That means 1/24 of your field of view. That light beam goes to an image slicer. That's 2 sets of 48 mirrors. That redirects 1/48 of that 1/24th image of your galaxy through a series of lenses, through a disperser, and then the dispersed spectrum is imaged on a CCD. And the CCD pixel scale is like 0.2 arc seconds. And that's how it works. And then you tie everything together, and that is an IFU that can image a galaxy in a single shot with no moving parts, with the exception of the field derotator. Anyway, here's some footage of the commissioning. It's the largest instrument ever installed on the Very Large Telescope. I won't get into that, but I'll just now show off some data and then end with a description, a little tutorial that I've made that I can send you a link for like if you want to play around with some MUSE data, which I think is really cool. So the rest of the talk, you can just sit back and watch pretty movies. So with a 1 by 1 arc minute field of view, this becomes trivial. You have only 9 pointings across the entire nebula. The instrument is super efficient. It's the highest throughput spectrograph on the entire mountain. There are 16 instruments on the Very Large Telescope, many of which are slit spectrographs. And an IFU has a higher throughput than a slit spectrograph, which is pretty astonishing. And so each of these exposures is something like 20 seconds, which gives you a 45 gigabyte cube. I'm stepping through H alpha plus N2 in the cube right now. And if you can actually explore this cube, it's really remarkable. So this is the actual cube. This is not just an image. This is 880,000 spectra. And I've taken slices of the cube at like basically red, green, or V-band, I think. Yeah, I've taken a red, green, and blue slice and stacked them, and you get this beautiful image. Same thing here. You would be forgiven if you thought that this was like a nice ground-based imager on an 8-meter class telescope, but this is 2.7 million individual spectra at 5 seconds per exposure. We've come a long way from this is the first photograph of the Orion Nebula, and now we have that. So here's one of my favorite sources. This is, of course, ESO 137, which is falling into a galaxy cluster, Abell something something. And as it's doing so, it's this edge-on late-type galaxy. Its ISM is being stripped out by ram pressure stripping. And so it creates this beautiful 80 kiloparsec long H-alpha tail here. So H-alpha is in pink, and then the Chandra X-ray tail is in blue. Just really stunning, but huge on the sky, right? A couple of arc minutes across, 80 kiloparsecs in physical space, and it's only 2 pointings with MUSE. So this is H-alpha plus N2 velocity structure again. So you see the galaxy light up here, and then the material that's stripped off light up. And you can see that it too is rotating. And so as the ISM is being stripped out of the galaxy, it keeps its angular momentum, of course. And so it's rotating like a corkscrew as it's being stripped out of the galaxy. Planetary nebula, I made this slide for Rudy. These become really easy, right? Planetary nebula in the Milky Way are huge on the sky, but it's not a problem. This is I think this is the Saturn Nebula. Here it is with MUSE, just a single pointing. I forget which lines I made for this one. I think that this one might be H-alpha and N2, or it might be O3, I can't remember. But really a lovely, lovely data set too. All of this is public, by the way, and I can give you links on. When you take multi-epoch observations with MUSE, you have effectively a 4-dimensional data set. You have 2 dimensions of space, one of wavelength and one of time. So this was one of our early observations during commissioning and science verification. This is a transit of Europa across the surface, and you can do absorption spectroscopy through potential water geysers ejected from cryovolcanism in Europa. And okay, I'll wrap up with my favorite cube that MUSE has ever taken. This is, of course, the Cartwheel Galaxy. I'm sure you're all familiar with collisional ring galaxies. The idea is that you have a late-type galaxy that's face-on like a bullseye, and a smaller companion like a bullet comes in and hits the center of the bullseye and passes through it. So as the companion approaches, you have a radial inflow of material as the stars and gas in the galaxy sense the approach of the incoming companion. And then as the companion punches through the late-type galaxy, like through the center of the bullseye, you get a recoil. And so you get this radially outflowing azimuthal ring here, and you pile up a lot of molecular gas and you form a little mini starburst along this ring. So here's just one pointing with MUSE, H-alpha plus N2 velocity structure again. Really, really spectacular data set, right? And this is not just for making pretty movies. Like, there is a lot of science you can do because you simultaneously image from just blueward of H beta to redward of H alpha. And so you can do things like spatially resolved Balmer decrements for extinction and spatially resolved electron density and star formation rate surface density, things like that, right? Anyway, I put this is cool. This is the first simulation of the cartwheel by Chris Mihos, who did it here with Lars Hernquist in 1994. I thought that was pretty cool. Anyway, I'm going to wrap up because I think, I'm basically out of time. But in an effort to get people more familiar with an IFU cube, if you've never used one before, I co-founded the Close AGN Reference Survey with my buddy Bernd Husemann, who's now at NPIA. So the CARS is now, it started as a MUSE survey of 40 nearby type 1 AGN. The data are spectacular, and they were so spectacular that we ended up proposing for tons of ancillary multi-wavelength data, including deep Chandra observations and HST, and now ALMA, which is really, really exciting. And so this has become a really, really exquisite multi-wavelength data set, which it also gives us the kinematics of like multiple gas temperature phases in the galaxy. And so we've had a couple of PhD theses written from it, and it's really exciting. Check out our website, carsurvey.org. I will basically skip through this, but for CARS, for MUSE, we've created high-level data products. So a MUSE cube is complicated. A MUSE cube of a galaxy is complicated, right? Because you have the stars and the gas. And what we've done is we've created a series of codes which, let me show you an example. Okay, so MUSE images both the stars, the stellar continuum, and the gas in the galaxy, right? And so what you can do with is run a Bayesian fit for every spaxel in the image on the stellar continuum, subtract that from every spaxel, and then what you're left are residuals, which are the nebular emission, the gas in the galaxy. Then you fit that nebular emission with a chain of linked Gaussians, and then what you end up doing is you very cleanly decouple the stellar component from the galaxy from the nebular component of the galaxy. And so we've provided those high-level data products to the community along with a series of codes to analyze them. And very importantly for these type 1 AGN, you're dominated by a quasar point source in the center, which is a point source in every channel in the IFU cube. So we've deblended those to really increase the dynamic range. And so you can have this, in the unreduced cube, you have this, you're swamped by this quasar PSF. Then you remove it, and you get this beautiful gas motion way down in the nucleus that you would have never otherwise seen. OK, so I will end with just showing off the CARS is now really becoming an ALMA and MUSE survey. And doing the two together is really, really powerful. So there's the MUSE H alpha plus N2 velocity structure up top. This is the ALMA map of CO2 to 1, that's cold molecular gas, along the bar. So this, for example, this is velocity along what is clearly X1 orbits along the bar, right? And if you know anything, the X1 orbit is a really beautiful thing to see. So this is effectively gas inflowing toward the nucleus as it's torqued by the bar. Here's another one, more ALMA data compared with MUSE data. Oh, I think my movie didn't play. Yeah, there's H alpha again and molecular gas side by side. Here's some more H alpha. So you can trivially create velocity maps and velocity dispersion maps. And how do you do this? I've created a tutorial, which I posted on GitHub, which shows you how to download some sample data, and then you go through this. It's a Jupyter notebook, so it's in Python. It uses AstroPy a lot. And if you're interested in playing around with MUSE cubes, you can check it out. It's for free, obviously. And it shows you how to make things like stellar velocity maps from our high-level data products and make these like pretty movies that I was showing. And yeah, I think I'll just stop there. Yeah. Yeah. Well, so the optical path isn't that complicated in terms of, and then the surfaces are really expensive and super clean and so super efficient. And so the optical path, although there are a number of reflections, it's just not super lossy. And you also, I mean, yeah, it's just not super lossy. It's more efficient than X-Shooter, which is previously the most efficient spectrograph, which is this super, this super clean slit, which passes to 3 arms. It's more efficient than that. So this beautifully high signal to noise observation, I think that was 600 seconds. You do a small dither in a field rotation, so that's 300 seconds per exposure. That's pretty incredible.
Yeah, I was going to ask about sky subtraction.
Yeah. Okay. Yeah. So what happens is, so if you're looking at like M87, which totally fills the field of view, then you need to do an offset to a blank sky. Most of the sources, or a lot of the sources, won't fill the field of view because it's 1 by 1 arc minute. And so what the pipeline, I didn't brag about the pipeline. Pipeline's awesome. Data reduction is trivial. You basically press a button. It's a little more complicated than that, but I can show you how to do it. If you have MUSE data, just come to me and I'll show you how to do it. But basically, if you have blank sky, the pipeline knows that. It will look at the blank sky and then fit a model to that blank sky and then subtract it from every spaxel. That works okay until you get about redward of 8,000 when you start getting swamped with tellurics. And so as part of CARS, we've developed a principal component analysis technique, which goes through it again and subtracts off the residuals after that process. And you get this really lovely, clean sky subtraction. It's really good. It's really good.
So Grant, you said the field of view is 1 arc minute, but if you said this, I missed it, I'm sorry, but what is the effective pixel size of the region I can get an independent spectrum?
Yep, 0.2 arc seconds. Yep, so MUSE has so this is the wide field mode, MUSE 1 by 1 arc minute. MUSE is newly commissioning a narrow field mode to be used with a new adaptive optics facility, GRON. This is deformable secondary mirror, which is being installed on Unit Telescope 4. Astonishing. You could, in principle, get down to a PSF full width half max of 0.05 arcseconds. In you know, kind of the best AO conditions with a really good Strel. Yeah, so and then you have some issues. You have some issues about whether you're sampling the PSF properly and stuff like that. But the pixel size point to arcseconds. This is a seeing limited observation. That's like 0.8 arcseconds.
Sorry, I was actually having a conversation with Max and Mark a bit yesterday,
yeah,
which brought up an issue that MUSE might be a solution to.
Yeah.
And that is that we wanted to do velocity mapping in Cygnus A. The problem is Cygnus A is in the galactic plane, and star separation is a nightmare. We've actually...
Yeah.
I mean, we've looked at this, and essentially, you know...
It's riddled with Milky Way stars.
Yeah, I mean, I haven't really thought it, but the point is that it's going to be really hard to separate.
Yeah.
But the field of view is not a lot MUSE fields of view, and if it's as efficient as you say,
it's super efficient. Right? What's the declination? So we go to plus 24 at most. So I think Cygnus A is too north, right?
It might be, yeah.
Which is why it's never been observed with VLT, I think. Right?
You're probably right. I
think it's too north. I'll have to look.
No, okay.
Yeah, so we go to plus 24.
Yeah, all right. Okay.
Yeah.
All right.
MUSE would solve it.
Yeah. No, whether can we get time? That's the thing. I mean, anyway. But I'll have a look. I mean,
so another option in the north would be Sitel on CFHT. It's not as good as MUSE, frankly, but it has an enormous field of view. It has 13 by 13 arc minutes. It's a fast Fourier transform. And if you only want to subtract off Milky Way stars, like Sitel can totally do it because the spectrum will be obvious.
Yeah. Okay. All right.
Might be. We should chat. We should chat because
I will have a look. The point is that you know, it's clearly a merger, but it's a real pain figuring out what's going on.
Yeah.
And I don't know if I've discussed the X-ray images, but we see what looks like, you see the merger shock essentially in the process of enveloping the core, so there's a sort of cool dent around, you know, so it really is overrunning the core, just enveloping it. But without dynamics, it's, I mean, it's like, I can't remember, there are 40 galaxies or something, Phrason or something years ago, but it's impossible, it's really difficult to do. Anyway, all right. Okay.
We'll chat about it. Anna. Thanks, I was just showing you. Thank you.